browse through all the constituent parts, the uh, modules that the Anaconda provides us. For example, here, we can see here Jupyter Notebook and Spider. These two are very important for us in order to code, and those who are familiar with VS Code, they can get into that one. And other things are there which, whenever required, we can make use of it. Yeah. So once it is installed, I would like to just already I have. There is Anaconda prompt. So in Anaconda 364-bit, we are seeing Anaconda prompt, and this is where we have to get inside. And through Anaconda prompt, I was saying first we have to create Conda environment and then try to install all our packages into that one. So I have already created. Now that's why I'm activating one of my uh, Conda environment. So I have created one environment with unit 1, so which I have activated. So I can see all my packages which are uh, already installed in this particular environment. Now this is specific. Um, these all packages are specific to this environment. So whenever we don't need the packages, we can uninstall it, and we can upgrade the uh, version, and we can have a very customized environment where we keep only the packages which are needed for us. Okay, so that was the thing, and so we come into we'll see a couple of programs where we were seeing yesterday. So I think we were seeing some exclusive OR get, which is not a linearly separable case. Um, so we need to have it's a nonlinear separable case wherein we use here multi-layer perceptron in order to train the classifier to learn for exclusive OR. For example, here the inputs were initialized with the logic we know, like zero, the for two input case, and then we know the expected output out of it, and the MLP is imported from a scalar neural network MLP classifier, and then we have to first give an activation function from yesterday's discussion. So I have used your tanh as the activation function, and then the number of iterations and the size of the hidden layers. And the most importantly, now here the model is specified. Then the model is given the inputs and with the labels. Now this will act as the label. The y-ops will act as labels, and this particular inputs, x inputs, will be learning based on the label. So label is something which we are clearly saying that for 0 0 input, the output has to be 0, and whenever both the logics are are either low or either high, the output has to be 0. Now we are clearly specifying that. That's the point of label here, and then you can check the score. Now this is the most important part. We are exposing our input to the model. So the model is created, but it does not know what are the inputs. So here we are exposing it, and with the labels. Now this model, the name is same again. We have not changed. The model here in this particular line has become a learned classifier model for exclusive OR get. Now once it has learned, we can test how good it has learned. So the score is that means it's a like giving again the same inputs and testing for the outputs. So during this in this step, it has to identify correctly for all the given inputs with respect to the label. So if it does so, the score will be high of 1, and if it does not so, So it will be the proportion of the out all the outputs. Now, how many corrects it has done and how many wrongs it has uh, come. I mean, how many correct wrong outputs it has given. So that was about the score, and the next is model.predict. Now, this will predict the outputs or the labels for us for given inputs. Now, here again, we are giving the same inputs and then we are getting the output. So at that particular line, we get the predictions like 0, 1, 1, 0 if it has correctly learned and is providing the outputs. So these are the steps, basic steps needed in order to construct one classifier model and then feed inputs to it. Now this is supervised learning. So why? Because we are giving the labels as the reference. So if we are not giving any reference, then it becomes unsupervised learning, machine learning method. Now those are like clustering techniques, for example, k-means and fuzzy c-means, and uh, followed by a lot of algorithms which comes under the genre of unsupervised learning. Now, whereas MLP is basically here, we are using it as a supervised learning method by exposing it to the labels, the reference. Uh, I just try to show an output for, yeah. So I just run this code and I've changed the activation function from TANH to ReLU and logistic. Logistic is the sigmoid activation function what we were seeing yesterday. And I just wanted to compare here now what is the influence of activation function. So it turned out to be there is an influence. So the TANH is giving exact response, and with ReLU again it's giving perfect output, whereas sigmoid and it does not mean every time it's 50% reliable. Sometimes it may change and we may have 0.75 or even 1. So that's a basic way of customizing a basic classifier, and this we are doing it here for a nonlinear example case wherein we know that if we could not come up with a linear separation for given input into the classes what we need, then we need to go for machine learning which implements nonlinear. So there it makes use of the back propagation and try to learn the weights and generate and build a classifier. Now, whereas always in classifier, the thing is it should have a very definite decision boundary. So one more classifier model is a linear regression model. Now these are very basic. In order to understand any complex algorithms or machine learning techniques in the future, so it's best to have the very basic mechanism how the classifier actually works and how a classifier has to be built, constructed, and then how actually the learning happens. Now, in order to uh, explain that. Now here, this is again very basic classifier model, and it is a linear regression. So as we have the most famous line equation, y is equal to mx plus c. So it works based on learning based on the given input. So it tries to find the relationship between the input variables and the response variable. So basically, uh, the equation is of this form, where the w's are the coefficients and w naught being the y-intercept, and w's are nothing but the slopes. Those are found for each data point. And then here the strict requirement is that the target value is expected to be the linear combination of the features, which means also there has to be a trend which is linearly increasing. Now, if it does not satisfy this, so linear regression completely fails in those conditions. So in mathematically, we can say uh, it tries to learn based on minimization of this factor, where y is the observed the actual label, and x o x w here is the actually learned w will be the learned weights in the model, and x is the inputs. So this is actually the predicted outputs from the model. So the predicted model and the expected value. So this difference is found in terms of norm. So we had very good discussion, uh, explanation about norms by professor. So the here the norm 2 is taken, and based on that, it's also a residual difference, which means we are seeing it's a subtracted value, and then it is squared, and then this particular norm is expected to be minimum. So when the minimum of this happens, now at that particular points, the line equation is selected to be the most appropriate uh, for the classification. So in order to, yeah, if the data is not behaving in a linear fashion, then we have to go for the classifiers which help us in overcoming this problem with nonlinear kernels. And the classifiers, one more discussion the professor was saying is to project the data onto higher dimensions. So here we are having a two-dimensional. So when it is projected on higher dimensions, the job of classification in those cases where the data is non-linearly organized, it can be possible. For example, we'll try to see one case of okay. So this is a logistic regression which learns based on the statistics from the data. So here this is the decision boundary which the model has created. Now we can see so there are two sets of data. So this purple color belongs to one's class, and the red dots belongs to the another class. So the model was able to generate one decision boundary which classifies the given input into two classes, but some of the data which belongs to the class represented by purple here also can be found in the other side, and the data of the other class can also be seen here. So these are the cases where uh, even the stringent classifiers are to be required in order to learn the features. So we'll see one example when we start from basic image perspective. Now, when how the information from the image is transformed into features, and then how we could use those features as inputs to the classifier. Okay, so yeah, just before that, one example of Fourier transform in Python, I just wanted to share. So from SciPy again, there are there is a package FFT pack, so from which we can get the required modules or functions for carrying out the Fourier transform in 1D as well as 2-dimensional. So Gravel here is an image. So what I want to share here is the same thing what we use in similar kind of thing what we use in MATLAB is here, like, but only thing being the FFTN is a function in SciPy. So that's why the SciPy is also very helpful in computation. It's for scientific computation. So FFTN of W image. Now here, this is the image. So image is actually first here. Sorry, the image Gravel. So it is transformed. It is filtered with the difference of Gaussians, and so this particular filtered image here is given as input to the FFTN, and then the magnitude of the Fourier coefficients is taken because we are interested in the magnitude. So NP dot ABS. So this is what the relation between different packages. So FFTN is from SciPy, and then NP dot ABS is from NumPy. So we take the magnitude from the coefficients, and FFT shift, as we know that in Fourier transform we need to, after the processing, in order to visualize the coefficients at the origin, we shift it. So that's why for this particular image, yeah. So for this Gravel image, we are seeing the magnitude, which is in for the original image, magnitudes are centered around here, and after filtering, the magnitude has, you can see the frequency components at different regions as well, different frequency now this is mainly because the image is filtered. So okay, so the point was here to introduce the Fourier domain. So this again the same example. Okay, now we take some. So yeah, so just wanted to share a couple of the basic methods what we use in image processing through the Python. So here we have the original image, which is the cameraman again. So the histogram of the image, and in the image, so there is one line. So this is from Atsu threshold. So one of the classic thresholding method in image processing is definitely Atsu threshold. So many times we may not uh, recognize it to be very useful, but in order to start off any segmentation method, it's very important that we start with Atsu threshold. So why? Because it tries to get some optimal value from the histogram. So this is the histogram. So here we have uh, definitely two regions. One region, a lot of pixels are centered around this particular intensity here, and